In this video, I wanted to talk about saturation as it regards to op amps. This is something that we are not going to need to deal with in the lecture. In the lecture, we are dealing with ideal op amps that have no problem no matter what voltages you input onto them. However, for an actual physical op amp, there is something that you have to worry about when dealing with it. And really quickly here, if I draw the diagram of our op amp, right? And remember, inside there was this voltage source here, which has a multiple A times VD. So the thing is you have this extra source that's inside the op amp, and that is providing power to the output. Because if you look at the picture, the output is not directly connected to the input. So there has to be something else there that is giving the power to the output, and that's this, dependent voltage source in here. What that means is there has to be something else that's actually powering the op amp that's not one of the three terminals. You have to give it power somehow. And what you're going to see on an actual op amp is you're going to have more than just three terminals. In this case, we're going to have two more for 5. The actual op amps you buy normally have 8, and the other 3 are for something else. But for right now, at least, we're going to focus on the other 2. These are going to be providing power for the op amp. This is what's going to make the op amp actually work. If you don't hook those up, then your op amp is not going to actually do anything. However, there is going to be a limit, because these are the things that are providing the voltage on the output. If, for example, you hook up the voltage here of 10 volts, and that's what's providing the output, that means your output would never actually reach anything past 10 volts. It couldn't get to 15 volts because it's not being provided at 15 volts. It could get anything less. It can get, say, 5 volts or 8 volts or 2 volts. Those are possible. But you can't go any higher than what you have there. And we also can't go any lower than whatever we hook up to the bottom. Now, in this particular diagram, I indicated it as negative VCC, so it'd be the same number, negative 10 volts here. But there's nothing wrong mathematically with hooking up, say, a positive 20 volts and a negative 40 volts. They don't have to be the same number, but it's a little easier to graph it this way. So what's going to happen here on your graph for what the output's going to look like based on the input here is, for the middle part of this, it's going to be a nice straight line. It's going to be a multiple of the input voltage. Maybe that slope is 2, maybe that slope is 5. It just depends on the specific op amp and setup you have. But whenever your output is going to reach the max VCC, it's from then on, it's going to flatten out and never going to increase anymore, because it physically can't. Similarly, when it gets down to the lowest value of voltage it could ever get to, it's again going to flatten out because it can't get any lower than that. And so these are called the saturation limits, or the saturation region of the op amp. And in lab, we're going to actually measure and see these things here. And like I said, in the lecture class, we don't ever deal with this. We just assume in the lecture class that you have enough voltage on your power supply that you can go on forever here. It's not physically realizable, but we're not worried about that right now. I just wanted to show you that this is something that can happen, and it will happen anytime you're dealing with physical op amps.